Now next topic, that is cells in series and in parallel. Means when more than one cells are connected in the circuit. So if the cells are connected in series and when the cells are connected in parallel, then what will be the equivalent EMF that we have to understand. First, take cells in series. Suppose, as shown in the figure, two cells having EMF E1 and E2 with internal resistances R1 and R2 respectively are connected between two terminal A and C, and the current flowing through this combination, that is I, then this type of connection of the cells, that is series connection of the cells. Okay, suppose the equivalent EMF of this combination, that is E equivalent, and the equivalent internal resistance offered by these cells to the circuit, that is R equivalent, then we can represent the equivalent circuit as shown in this figure. Now, suppose here we take the terminals A, B, and C as shown in the figure in this connection. Then the potential difference between A and B, VAB, that is equal to VA minus VB, that we can write E1 minus IR1, because here the current I is flowing through the cells. And the potential difference across BC, that we can write VBC equal to VB minus VC, that is equal to E2 minus IR2. So resultant potential difference across AC, that we can write VAC, that is VA minus VC. Now here in this equation, add the potential at BVB and subtract VB. So we can rewrite this equation as VA minus VB plus VB minus VC. This VB cancelled after all this equation. But now VA minus VB, that you can write E1 minus IR1, and VB minus VC, that you can write E2 minus IR2. So VAC, say it is V, then that is equal to E1 minus IR1 plus E2 minus IR2. So we can rewrite this one as V equal to E1 plus E2 minus I into R1 plus R2. So we can compare this one with V equal to E minus IR. So we can write V, that is equal to E equivalent minus I into R equivalent. So here E equivalent, that is equal to E1 plus E2, and R equivalent, that is R1 plus R2. So if n cells are connected in series, then we can write the equivalent EMF of the series combination of the cells, that is E1 plus E2 plus E3 up to En, and R equivalent means the resultant internal resistance offered by this combination to the circuit, that is R1 plus R2 plus R3 up to Rn. Clear up to this one? Now here see, in this series combination, the cells are connected like this, positive, negative, then after positive, negative. So here in this case, we write E1 plus E2 plus E3 plus up to En. But suppose any cell is connected in opposite manner, it implies that for first cell positive, negative, and then after for second one, here negative terminal is there and positive terminal is on this side. So in that particular case, you have to write E1 minus E2 like that. So remember this thing, this E equivalent E1 plus E2 plus E3 up to En, that is the algebraic summation. Clear to all of you? Then after the cells in parallel. Now see, if two cells are connected between terminal A and C as shown in the figure, positive terminal of both the cells that is connected to A through B1 and negative terminal of both the cells that is connected to C here through B2. Then this type of combination of the cells that is known as parallel combination. If equivalent EMF of the combination, that is E equivalent, N, the equivalent internal resistance, that is R equivalent, then this is the equivalent circuit. Suppose here the total current constituted, that is I, and through cell E1 having internal resistance R1, the current flowing, that is I1, and through the cell of EMF E2 having internal resistance R2, the current flowing, that is I2. Then here the potential difference between B1 and B2, that we can write VB1 B2, the same one that is across A and C, because between A and B1 as well as between B2 and C, there is no other component. So whatever is the potential difference between B1, B2, the same one is there between A and C. So we can write VB1, B2, that is equal to VAC, and say it is V. Then for first cell having EMF E1 and internal resistance R1, we can write this potential difference V, that is E1 minus IR1. And for second cell, the same potential difference, that we can write E2 minus I2 R2. We know in parallel combination, for each component, the potential difference, that is always same one. Now, here total current I enter to this particular junction, and I1 and I2 are coming out from the junction. So we can write I, that is equal to I1 plus I2. Okay. Now, here we can write from these two equations, one equation, that is I1 R1, that is equal to E1 minus V. Therefore, I1 equal to E1 minus V upon R1, and another equation I2 R2, that is E2 minus V. So I2, that is equal to E2 minus V upon R2. Now substitute these values of I1 and I2 in this equation. So I, that is equal to E1 minus V upon R1 plus E2 minus V upon R2. Therefore, I that is equal to E1 upon R1 plus E2 upon R2 minus V upon R1 minus V upon R2. So I that is equal to E1 upon R1 plus E2 upon R2 minus V into 1 upon R1 plus 1 upon R2. Clear up to this one? Now, make this V into 1 upon R1 plus 1 upon R2 as a subject. So take it on left hand side and take this I on right hand side. So V into 1 upon R1 plus 1 upon R2, that is equal to this E1 upon R1 plus E2 upon R2 is directly written as R2 E1 plus R1 E2 upon R1 R2 minus I. Therefore, V into, here again R1 R2 is taken LCM. So R1 plus R2 upon R1 R2, that is equal to R2 E1 plus R1 E2 upon R1 R2. Now take this bracketed term on left hand side, that on right hand side. So V equal to R2 E1 plus R1 E2 upon R1 R2 into, now R1 R2 upon R1 plus R2 minus I into R1 R2 upon R1 plus R2. So this R1 R2 R1 R2 cancelled. So resultantly we can write therefore V that is equal to R2 E1 plus R1 E2 upon R1 plus R2, this one, minus I into R1 R2 upon R1 plus R2. Now compare this equation with V equal to E equivalent minus I into R equivalent. So we can write E equivalent, that is equal to R2 E1 plus R1 E2 upon R1 plus R2, and R equivalent, that is R1 R2 upon R1 plus R2. Clear to all of you up to this one? Now the equation of current is rewritten here. I equal to E1 upon R1 plus E2 upon R2 minus V into 1 upon R1 plus 1 upon R2. So we can write V into 1 upon R1 plus 1 upon R2, that is equal to E1 upon R1 plus E2 upon R2 minus I. Therefore, we can write V that is equal to, now without taking LCM, take this bracket on right hand side. So E1 upon R1 plus E2 upon R2 whole thing divided by 1 upon R1 plus 1 upon R2 minus I upon 1 upon R1 plus 1 upon R2. So this one is the equation for two cells connected in the parallel. But suppose n cells are connected in parallel, then we can extend this numerator here for first term like this. V equal to E1 upon R1 plus E2 upon R2 plus up to En upon Rn divided by 1 upon R1 plus 1 upon R2 plus 1 upon R3 up to 1 upon Rn minus I upon 1 upon R1 plus 1 upon R2 up to 1 upon Rn. But we know this thing. When we take cells in parallel, so at that time their internal resistances are also in parallel. And for parallel combination of resistances, we know the equation. This 1 upon R1 plus 1 upon R2 up to 1 upon Rn, that we can say it is 1 upon R equivalent. And this one is also 1 upon R equivalent. Clear? So here, now we can compare the same equation with V equal to E equivalent minus I upon 1 upon R equivalent like this. So for n cells in parallel, the equivalent EMF that will be given by this term E1 upon R1 plus E2 upon R2 up to En upon Rn, whole thing divided by 1 upon R equivalent. Clear to all of you? So in general, you can write for n cells in parallel, E equivalent, that is E1 upon R1 plus E2 upon R2 plus up to En upon Rn divided by 1 upon R1 plus 1 upon R2 up to 1 upon Rn. Now, whatever the number of cells are given to you in the parallel combination, you have to write up to that number of steps here. 3 સેલ આપ્યા હોય તો E3 upon R3 અને અહીંયા 1 upon R3 સુધી લખો. 5 સેલ આપ્યા હોય તો E5 upon R5 અને અહીંયા નીચે 1 upon R5 સુધી લખો. And the equivalent resistance, for that you can write the equation 1 upon R equivalent equal to 1 upon R1 plus 1 upon R2 up to 1 upon Rn. This is as per the parallel combination of resistors which we already discussed. Clear?